Good afternoon, everyone, and welcome to today's webinar, Embedded and Immersive Engineering from Amplify in the Lawrence Hall of Science. Thank you for taking time out of your busy days during these uncertain times to join us for today's webinar. My name is Heath Williams. I'm the Marketing Manager at Amplify Science, and today I'm joined by Rebecca Abbott and Leslie Stenger from the Learning Design Group at UC Berkeley's Lawrence Hall of Science. Rebecca and Leslie are on the professional development team at the Hall. In today's webinar, Rebecca and Leslie are going to show us how engineering is seamlessly integrated into the Amplify Science curriculum across grades K through 8, as we experience their cutting-edge approach to engineering and its connections to the NGSS. Before we get started, though, a couple of quick logistical notes for you. You're going to be on mute for the duration of this webinar, but we do want to hear from you. You'll notice a Q&A button on the bottom of your webinar screen. Drop any questions you have there as we go, and we'll leave time for a Q&A at the end of the session. This webinar is also being recorded. You'll receive a link to the recording in your inbox tomorrow to watch on demand or share with colleagues who couldn't make it today. So be on the lookout for that email tomorrow. All right, with that, let's go ahead and get started. And I'm going to hand it over to Rebecca and Leslie.
Great. Well, thank you, Heath, for those introductions. Welcome, everyone. Like Heath said, we're so glad you could take time out of your busy and new experiences to join us today for this webinar. It's called Embedded and Immersive Engineering, and my name is Rebecca, and I'm here with Leslie Stenger, and we're both curriculum designers and professional learning specialists. And what we do normally is work with teachers across the country who are implementing the new standards and who are using the Amplify Science curriculum. We are from the Lawrence Hall of Science, a public science center on the UC Berkeley campus, and we'll go to the next slide for this. And to share a little background about who we are, the Lawrence Hall of Science has been creating curriculum for nearly 50 years. Our group, which is called the Learning Design Group, has embarked on a project to create a K-8 science program designed from the ground up to meet the NGSS. So in order to do this, we initially got research grant funding from a variety of federal and local organizations to help us develop approaches that best meet the standards. And this funding also helped us to test this curriculum and this approach in a variety of classrooms, just to ensure that these materials and this approach is effective. And then we were able to turn that into a curriculum that educators out in the field, such as yourselves, can use. So what we've done is partnered with Amplify, and we are in deep collaboration with them, like Keith mentioned. They're a company who has a 15-year history in developing digital tools for teaching and learning. We've been able to create this K-8 science curriculum called Amplify Science. So essentially, we've taken the best of what the Lawrence knows about how students need to learn science deeply through doing and talking and reading and writing, and taken what Amplify knows from more than a decade of using technology to innovate teaching and learning to make the program that we are very excited about called Amplify Science. So now that you know some of our context, we're going to be sharing that research base and pedagogy with you using Amplify Science units as examples. And so in a few minutes, I will pass it to Leslie, but I do want to let you know what to expect in our session today. So overall, the goal of today's session is to explore generalizable principles of teaching and learning engineering, what this looks like in our curriculum, and how that reflects the vision of NGSS. So if you're a current Amplify Science user, this may help you understand some of the principles that undergird our design-focused units or our engineering units. And if you're not currently using Amplify Science, those principles will be generalizable across any design challenges. We want to make sure we answer your questions, so please do use the Q&A, as Heath mentioned, to ask us presenters questions, and I'll be mostly monitoring those while Leslie is presenting. And one thing to point out in our introductions is that if you're watching this live with us now, which a number of you are, or if you're watching the recording anytime spring 2020, Amplify does have a COVID-19 response page, and the URL is up on your screen. Amplify has other sessions devoted to this resource, and we'll post this resource in the chat as well. But we're not going to spend time and review details of this website in this particular session. So I did want to just make you aware of it in case you want to bookmark it or come back to it later. And we will return to some of these ideas about remote learning at the end of our session today. So with that, let's go ahead and look at our plan for the day. We are going to let's see, like I mentioned, what Leslie will start off by spending some time first just getting to know broadly what is engineering's role in the NGSS. What does it look like in teaching and learning? And then second, she'll get into how does this look in Amplify Science? And then I'll come back at the last part of the session, returning to applications and next steps, including some suggestions for the implications in remote learning situations that's in the forefront of all of our work right now. And at the end, we'll return back to the Q&A to answer your questions. All right, so I'll pass it off to Leslie with that.
All right, thank you, Rebecca. I'm very happy to be here today to talk with you about engineering and the NGSS and how engineering is integrated into Amplify Science. But before I get started, I just want to acknowledge this time that we're in and just say thank you to all the educators out there that are making learning happen for students across the country. So we appreciate it so much. But back to engineering, there are many shifts between previous national standards and the NGSS, but the significant increase in emphasis on engineering is one of the biggest. And so this quote from Appendix A of the NGSS captures this shift. It says, a significant difference in the next generation science standards is the integration of engineering and technology into the structure of science education. This integration is achieved by raising engineering design to the same level as scientific inquiry in classroom instruction when teaching science disciplines at all levels, and by giving core ideas of engineering and technology the same status as those in other major science disciplines. This emphasis includes both practices and disciplinary core ideas. And in terms of practices, all 8 practices can be involved in engineering, but there are 2 that have a special flavor for engineering: defining problems and designing solutions. In terms of disciplinary core ideas, as was mentioned in the quote, engineering and technology have been elevated to the same status as life, earth, and physical science. Students aren't just learning to engage in engineering practices, they are also learning about engineering as a discipline. So how do we accomplish these shifts? Before I talk about how we are doing this in Amplify Science, we first need to consider what we might be shifting from. In my experience as a middle school science teacher and an administrator, I love seeing students working on design challenges. So for example, like building the tallest tower out of straws or constructing a bridge out of toothpicks. When I would walk into a classroom and see these happening, I would see students who were engaged and collaborating to solve problems. However, the NGSS calls on us to push even further. And I want to talk about 4 important ways that we are doing this in Amplify Science. I'll introduce these now, and then I'll go more in depth into them with examples for each. And so, all of our units are driven by phenomena and problems that could exist in the real world. A goal of this part of the approach is to help students see how engineering is connected to their lives. Students may have a hard time understanding how towers made of straws and bridges made of toothpicks are related to solving problems in the real world. The second aspect is applying science understanding. So engineering problems are the perfect opportunity to let students apply ideas about life, earth, and physical science. In a design challenge, like a straw tower or toothpick bridge, the focus tends to be on the design and building as opposed to justifying design decisions based on science understanding. While these activities are engaging, they sometimes are a lost opportunity to let students deepen their understandings in the other domains by applying them in the context of engineering. Now, the NGSS call on us to provide our students opportunity to learn about a full range of engineering ideas and practices. In the kinds of projects I've been mentioning, the vast majority of the time is spent in the design and building phase of the design cycle with maybe a bit of testing. So the Amplify Science approach broadens the focus to include rich opportunities to analyze data and revise designs, as well as explore other ideas in engineering, like using models and controlling variables. In Amplify Science, students also take on the role of a variety of types of engineers. Building projects like the Tower and Bridge don't provide students with opportunities to see the full range of engineering that there are out there in the world and to be inspired by that range of real-world engineering careers. So I'm now going to show you a little bit more about each of these elements of engineering in Amplify Science. But first, I want to do a really quick overview of where you can find engineering in the Amplify Science program. As we mentioned, Amplify Science is a K-8 program, and these are the 21 units in grades K through 5. In these grades, we have a unit with a focus on engineering and design in each grade. In each of these units, students take on the role of some kind of engineer, and the practices of engineering design are made explicit to students. There are also another 6 units where students are engaging with engineering design in smaller ways. In the middle school program, there are 27 total units, 9 at each grade. This shows the units in our recommended integrated sequence, but they can also be taught in a domain sequence. Each grade has a launch unit that starts the year, 6 core units, and 2 engineering internships. This is an immersive experience where students take on the role of an engineering intern. The engineering internships always follow a core unit and give students a chance to apply what they learned in that unit to an engineering problem. For example, the phase change engineering internship follows our phase change unit. Now I want to go a little more in depth into the 4 approaches I mentioned at the beginning. The first one is connect to real-world problems and roles. Now in each unit, with an engineering focus, students take on the role of a specific kind of engineer and have a real-world problem to solve. For example, in the first grade unit, Light and Sound, students take on the role of light and sound engineers and design, test, and iterate upon scenery made with light and sound, which would be much easier for a puppet theater company to move to different places than standard wooden scenery. In the third grade unit, Environments and Survival, students are biomimicry engineers, and they learn about how biomimicry is the practice of using organisms' traits to inspire designs that solve problems. They work to design a robot that can pull up invasive plants and grind them up. And in one of our middle school engineering internships, Plate Motion, students in the role of geohazard engineers design a tsunami warning system to alert populations in the Indian Ocean of an impending natural disaster. Now, I mentioned that our middle school engineering internships are designed to be very immersive. So I want to tell you a little bit more about that. For each unit, students are working as an intern in a particular division of Futura Engineering. It's a fictional firm that's similar to Engineers Without Borders. In each internship, they have a project director who sends them a video message introducing them to the problem they are focusing on and the criteria they need to address. In this internship, Anton Green introduces the chemical engineering interns to their engineering project, designing portable baby incubators for low birth weight babies. Students then interact with their project director by sending and receiving messages in Futura Workspace, which is a kind of professional email system that allows Anton Green to send students assignments, for students to submit their designs and proposals, and for Anton Green to send them feedback. So to sum up this part of the approach, let's contrast what I talked about earlier, design challenges like straw towers and toothpick bridges that are common in classrooms. And the Amplify Science approach pushes beyond that to connect to real-world problems like invasive species or the need for a tsunami warning system, and it connects to real engineering roles. The second aspect of our approach is giving students a chance to apply science understandings in the context of engineering design. As I mentioned, engineering tests are the perfect opportunity for students to deepen their understanding of ideas from other domains. So every engineering task in an Amplify Science unit involves applying disciplinary core ideas from life, earth, or physical science. I'll share a couple examples. So in our third grade unit, here is one disciplinary core idea. And so in this environments and survival unit, students figure out how in any particular environment, some kind of organisms survive well and some survive less well. And this is because of particular traits and how they interact with or match with the environment. They apply what they figured out to design a robot based on actual animal traits. And this is called biomimicry. So they draw on their ideas about giraffe traits for neck and tooth structures and design a robot that has teeth that can remove and grind up invasive plants. In our middle school plate motion engineering internship, students have just finished a unit where they work to figure out this disciplinary core idea about natural hazards. They then apply ideas of plate boundaries, plate motion, and earthquakes that they figured out from the plate motion unit. And then they also use historical data about the frequency of different magnitudes of earthquakes along plate boundaries in the Indian Ocean region in order to design a successful tsunami warning system. This opportunity for application means students are learning the life, earth, and physical science concepts more deeply, and it is also modeling the relationship between science knowledge and the engineering process. In other words, in contrast to straw towers and toothpick bridges that often are content light, all of our engineering challenges are opportunities for students to apply key ideas from life, earth, or physical science. And this application gives students a chance to deepen their understanding. The third principle is to emphasize a full range of engineering ideas and practices. Typical approaches sometimes seem to equate engineering with constructing things, but the engineering disciplinary core ideas go well beyond that. First of all, the design cycle is an essential practice of engineering, but it takes some careful curriculum design to make sure there's time for students to iterate on their designs. And I'll talk about one technique we have for that in a moment. But first, I want to share one way we are integrating a full range of engineering ideas and practices, not just the design cycle. At middle school, we've taken the engineering disciplinary core ideas and broken them down into these 6 emphases. Each internship focuses on one of these concepts in depth. So for example, the idea of trade-offs is a really important concept in engineering. And the students are introduced to this concept through an engineering tip video shown here, where the CEO of Futura Workspace uses an example of designing bicycle helmets that are light and cheap. And she talks about the kind of trade-offs you might have to make in order to come up with an optimal design. Students then apply these ideas about trade-offs in their own design. Returning to the design cycle, it's hard to give students a chance to go through multiple design cycles. For example, if you remember that toothpick bridge, if your students spent 3 or 4 days building a toothpick bridge, it's unlikely that you'd want to give them another 4, 5, 6 days to do more iterations on their design. We help them address that problem with digital design tools. Here are a couple of examples. Students design physical designs too, but they use digital design tools to be able to rapidly test, analyze, and revise their designs. In the grade 3 unit, Environments and Survival, the students use this RoboGrazer design tool to test their ideas about their robot. In the middle school Force and Motion engineering internship, students use this design tool to iteratively test their designs for a supply pod that will deliver humanitarian aid packages to people in disaster-stricken locations. And so I want to give you a chance to sort of see the power of this design tool in helping students have opportunities to iterate on designs. And so I'm going to swipe on over to the design tool. But first, I want to give you a little background. And so, as I said, that the students are challenged to come up with a design of how to deliver humanitarian aid packages to people who have experienced a disaster in hard to reach locations. And so they're given some constraints and criteria. And so the one constraint is that these are hard to reach locations, and so the supplies need to be delivered by helicopter. And so these pods that they need to design have also certain criteria. They need to minimize cargo damage, maximize shell condition, and keep costs low. So after doing some research on the materials the students have to work with, and then also revisiting some of the ideas that they figured out about force and collision in the previous force and motion unit, students are ready to begin the design cycle. And so they're encouraged to make a plan. So I'm going to make a plan I know that if I can have a low mass cargo pod, then that might help minimize the cargo damage and maximize the shell condition. So I'm going to choose a shell that is very low in mass. So I'm going to choose fiberglass as my shell. Then I'm going to go down here and check out the padding materials that I can use. And so you can see there are a number of different options for padding, but I see that good old packing peanuts are the lowest mass. So I'm going to fill my pod with packing peanuts. And I can see that there are a couple other add-ons. I can put something on the top, like a flap or a parachute. I could put something on the bottom, like foam blocks or springs. But since I'm really trying to get very low mass, I'm not going to add anything. So I'm going to go with just that, the filling and that fiberglass shell. So I'm going to test my design and see how we do. Here we go. And wow, that doesn't look like it turned out so well. I wanted to maximize my shell condition. And when it starts, it's a waterproof container that people can actually use for shelter. But it looks like mine didn't do so well. And my cargo damaged almost a third. But the great thing is I can think about, well, what else do I need to do? And I can do a new design. So I'm going to go back. I'm going to think about, if I add on something, I can also reduce the velocity. So I'll try a low mass parachute and test that out, see if that makes a difference. Oh, and I can see it made a huge difference. I now have a shade-only shelter and my cargo damage got reduced tremendously. So as you can see, students can plan, test, analyze, and then make a new plan going through that design cycle very easily as they try to meet the criteria and come up with an optimal design. So I'm going to go back to my slides. And so in summary, while towers of straw design challenges place most of the emphasis on the building phase of the design cycle, in the Amplify Science approach, students experience the full design cycle, and key disciplinary core ideas about engineering are carefully integrated. That brings me to my fourth and final principle: model and inspire engineering careers. In addition to tackling design challenges with hands-on materials, there are nearly a dozen books across K-5 that model, support, and inspire students in their engineering design work. For example, we have books that model how an engineer does her work. These books model practices from the big, like iterative design, to the small, like ways of displaying data. But they also model dispositions, including how engineers may react to missteps and disappointment with persistence and approaching things differently. These books feature a wide range of inventors and engineers, and even feature kid engineers. There are also books that are designed to fascinate and inspire students to want to be engineers. For example, the book Cockroach Robots is about a team of biomimicry engineers who build robots inspired by the traits of organisms. This book follows the process of designing a many-legged robot that can run fast through tiny spaces, just like a cockroach can. These robots are designed to enter buildings in the case of a disaster, such as an earthquake, to see if it is safe for people to enter the buildings. Cool in Hot Places shows the many solutions that humans have designed to keep cool in hot places. At middle school, students read science articles about a variety of engineers, and about engineering careers that relate to their role in the unit. Another important aspect of this approach is we worked really hard to make sure we showed the range of engineers. Typical programs tend to only represent engineering that involves building, like bridges and towers. We included food engineers, geohazard engineers, biomedical engineers to make sure that students see the full range of types of engineering and types of careers. So to sum up this fourth aspect of our approach, we ensure that students are exposed to all kinds of engineering throughout our units, and we include books and articles that show engineers in action in the real world. The NGSS call on us to forefront the practices and discipline of engineering, but the NGSS are not a curriculum. And so we hope you found these examples helpful for how the practices and discipline of engineering can be enacted in a curriculum and in a classroom. So now I'm going to hand it back over to Rebecca.
Great, thank you, Leslie. Those were all great points. And so we hope we've provided you with some broad ideas about how teaching and learning and engineering may look or feel differently in this era of when we're instituting the NGSS or the next generation science standards. So let's take a couple minutes to discuss the applications in our own context. So first, if you are an Amplify Science teacher, meaning you currently use the program, this may be a good moment to try out an Amplify Science engineering unit. For example, if you teach middle school, there's 2 engineering internships in each grade level. If your students have access to digital devices while they're learning at home, the engineering internships are really good contexts for you to have students engage with. Like we said, they can take on this role of an engineer. They can get their assignments through the project director at the fictional company of future engineering, and they can submit their assignments digitally. And if you're teaching elementary, there is 1 unit in every elementary grade that's a design unit where the students take on the role of an engineer. Students can do a lot of the research, the planning, and the designing with materials that can be found at home, so it may be a good chance to have students be active designers at home. But if you are not using Amplify Science for everyone, you can start to think about how you can apply some or all of these principles in any engineering challenge you're having students do. So we suggest that you modify what you're currently thinking about doing for engineering challenges in terms of keeping these principles in mind. This is how we all start to make the shift from a typical approach where it's the do phase to an NGSS aligned approach that includes all of these components. So as we close the session, we just wanted to make sure that we've provided you with some links from Amplify to help support you in this moment of distance learning and remote teaching and learning. These first 2 sites that you see on the screen here are from Amplify. The first one I'll talk about for a second is called the Remote Learning site, and there are print and digital resources here, and this is the one I showed at the very beginning. Now, this isn't just for if you're teaching Amplify Science, this is for all teachers and all students to be able to use the curriculum. So it includes having a shared login to use during this time, which is helpful if you are an Amplify Science teacher, and we know that many students have either forgotten their logins or they can't get in for some reason. They can use a general login that Amplify is providing for free. But if you currently don't have Amplify Science, it might be a good chance to check out some of the resources like simulations and some of the lessons. I will give a quick heads up and a warning though, if you're not super familiar with Amplify Science, it is a very comprehensive curriculum meant to be a core curriculum. It's not just supplemental individual lessons. So if you are already feeling overwhelmed and don't want to take on something completely new, that's understandable. But it may be worth a peek just to see if there's something that is of use. And this site, again, is the remote learning site, the first bullet. The second bullet that's listed with free resources there, what those are is a set of lesson videos from the program. We've partnered with a couple of schools and a couple of districts in Denver and Seattle to start creating lesson videos, and more are going to be added each week as the project continues. And the third source that you see there, wideopenschool.org, this is a site not by Amplify, but by Common Sense Media. And what it is it provides a variety of open source materials for learning, not just in science, but across curriculum areas. And Amplify is super proud to be a partner in this project as well. And finally, this last piece here, there is a dedicated email help desk for those of you who are teaching with Amplify Science right now. Many of the districts that you work in are already in touch with someone at Amplify in order to help you and support you make this incredible transition at this time. But if you individually or if your district needs to get in touch, that is the best place to email. Okay, so that brings us to the end of our session. I am going to go on to the Q&A, and there are a few questions that have already popped up in the chat. And then I'll go ahead and start to respond to. But if you haven't gotten a chance to put in your question yet and want to now, we'll go ahead and answer those as they come in. One of them came in talking specifically about the supply pod experience that Leslie led you through. And the question was, how much of that was digital? And so I accidentally moved that question over, but I just want to respond to live. But the question is, do the students do the digital before or after building? So the way those engineering internships works is the iterative design work all happens in the digital tool. So what Leslie showed you is essentially what students would do. They don't make a physical supply pod during that phase of the unit. However, before that point in the unit, they will have made an egg drop. That's a classic experience that many of us are familiar with. And what the students do is they make that egg drop and they see what happens in terms of using different materials and using physical materials to drop the egg. And that's part of what we call the research phase before they move on to their next phase, which is their iterative design phase. All right, another question. And there's someone who responded to that same question too, is that they do their design first and then do the egg drop. That's interesting, to make better egg drop design. So that's a really nice way to see, to apply and do another application of your iterative design. So thank you for that comment. All right, another question here. How does that example of protecting the cargo make sure students are using DCI content rather than just unstructured trial and error? That's a really good question. What types of questions, prompts are used to ensure that a deeper understanding is developed by all students? Yeah, that's an excellent question. And that is something that we've worked in our research phase to really target. We actually have someone here on our staff who is analyzing student responses in the design tool. And he's like a coder, and he has this amazing way that he's tracking that. And that's one way that we internally are improving, our units, is by doing exactly what you mentioned, is that, we don't just poke around and try one thing and go back. So the unit itself is designed not just to have students do trial and error, but supports them with a few different tools. First of all, they do a design and planning and testing tool, and students have to justify some of the ways that they're making changes to their design. And that's a place where it does make student thinking and student learning visible in terms of, are they applying their ideas about forces, collision, velocity, and mass? Those are the DCI content pieces to their changing designs. Can they see where a mistake was made or where something was less than optimal and make a change based on those principles? And so we don't want students to just go back and change one thing at a time and trial and error, like you mentioned. And so there's a teacher's guide that has lesson by lesson, anticipating exactly what you mentioned, helping the teacher, give the support to the teacher that they need. It's not just happening over one session, it happens over multiple days. All right, so hopefully that answered that question. There is another question, and this is maybe more for Heath, but it says, can we provide a continuing education certificate? We know some folks are needing this for some of their CEUs right now.
Yes, I was just typing an answer to that question. If you email me at hwilliams@amplify.com, I can get a certificate to you if you need it. Any email you received about this webinar has my email address in it. So just shoot me an email and say you need a certificate for today's webinar, and I can get you one.
Okay, I'm checking Q&A and I don't see any other questions at the moment. Oh wait, one more just came in. Let me read that for a sec. Okay, great. So yeah, someone's asking about, and maybe Leslie has a response to this as well, but the question is, how do you incorporate the science and engineering practice elements that are engineering focused? So the question is not just about the DCIs that are engineering focused, but also about the practices that are engineering focused. And she gave a good example. Define a design problem that can be solved through the development of an object, a tool or process system. It includes multiple criteria and constraints, including scientific knowledge. So I would say that particular SEP that you typed in, Lauren, is exactly how these units are designed, that we include criteria from the very beginning, and that we have them having, saying, well, you've got a problem, and so how can we define that design problem and use our engineering practices in order to provide a solution. And so those elements are built into the design of the units themselves, and we give students very explicit opportunities to engage in those practices as they're also meeting the engineering and content criteria. Anything else to add with those? It's a really good question. All of our units are are, like we mentioned from the beginning, have been designed for NGSS. We did not retrofit old engineering or design challenges to meet the designs of the NGSS. So we had the NGSS in front of us, I think as early as it came out, 2011, 12, 13, before it was actually out in many states, and we were using that to design our program. So that helps everyone be reassured that they are three-dimensional from the ground up. And we have that documentation in every unit to help support when and how you're meeting those standards. Another question just popped up. Are there engineering units available in Spanish? Yes, all of the Amplify Science units are both in Spanish and in English. We have had that as an ongoing project, and at this point I believe that every unit, both student-facing materials and teacher-facing materials, are available in Spanish, including the engineering internships, which Heath is nodding about, so that is correct. All right, and just a thank you from a former GEMS user. Yes, someone knows that the Learning Design Group as a former, as our project has continued to grow. It started off with GEMS, which were some beloved materials back in the day that are still have a lot of utility. And then our project went to Seeds of Science, Roots of Reading, which was a primarily elementary program and has blossomed into the Amplify Science NGSS designed units that we have today. So thank you for those of you who stuck with us in our legacy. Are there any of the units in Arabic? No, they are not. However, there are bilingual glossaries, or not bilingual, but 10 languages represented in some of our glossaries, including Arabic.
The email address, I see a question in here, an email address to send to for a certificate. That would be me, hwilliams@amplify.com. That's H as in Henry at Amplify, H as in Henry Williams at amplify.com. Any email you received about this webinar, so the email with your join link, the email reminding you that it was happening, you'll see my email address in that email, so you can just click on it from that email and get it to me that way.
Another question that just came in was about tips for special needs students. A lot of our units are, again, because there's a gradual release of responsibility, meaning the teacher is working to support students all along the way, where we have them become more and more independent. So there are many opportunities that we don't just release the students to do these types of designs or this type of work independently, that there is plenty of opportunities to scaffold. That said, we do also offer in every unit, there are what we call differentiation notes, and in every lesson, in fact, we have ideas that are specific for each lesson about ways you can support students who need additional support. So those scaffolds are built in an embedded way, but there's also additional notes to the teacher for additional ideas for any of our units. Okay, so we'll go to the last slide here after the Q&A, but I think essentially we've gone through a lot of these questions, but thank you all for sticking around and joining us for this entire webinar. And I'll pass it back to Heath, who's going to close us out and let you know what to expect.
Yes, thank you so much for taking time out of your days today. I'm sure they are hectic in these crazy times. We enjoyed having you, and thank you, Rebecca and Leslie, for your expertise as always. I always learn something on these webinars too, so thank you. Like I said at the beginning of this session, you'll receive a link to the recording of this webinar in your inbox tomorrow. If you are needing a certificate, that's where you'll see my email address, and you can just shoot me an email from that email. So that will be coming to your inbox tomorrow. Thank you so much for joining us, and have a great rest of your day.
Bye, everyone.